Welcome to qnawire.
Now, this question we're looking at a diatomic molecule, and we are investigating the rotational energies associated with different kind of rotations. So we have two possible rotations over here. One is along the axis, that is joining the two atoms, right? And this basically is in this direction, right? And the other rotation is along the center of where the two atoms are connected, right? So that's another rotation axis. Now, typically, the axis of rotation about the joining, right, the line joining the two atoms is usually inaccessible, right? Because this, in order to rotate this molecule about this axis, the amount of energy required is very, very high. And we want to show that in this question. We want to show why. And we can start off, right? This is the other rotation axis. So, start off, we need to label the various axes. So, we are given in this question that this is the y-axis. And rotation about this is the x-axis. Now, to find the energy associated with the first excited state, this is equals to h bar square over 2i times j plus 1. So at the first excited state, this is when j is equals to 1. So we get 1 times 2, which is 2, and then we get h bar square over I. So the only difference between the two different kinds of rotations would be the moment of inertia of the molecules about the axis of rotation. Now for the first one, we're looking at y. For the moment of inertia around the y-axis, this is just spheres rotating, and we know that about the center of mass, and we know that the moment of inertia for spheres rotating about its center of mass is just 2/5 times m r squared, where r is the radius of the sphere. This is the r. Now this is for one of the sphere, and for the other, we add them up together, right, assuming that they are the same masses. So this is 4/5 mr squared. On the other hand, for the rotation about the x-axis, we're looking at the rotation about another axis. So the sphere doesn't rotate itself, but the entire center of mass rotates. So for this center of mass to rotate, we treat it like a point mass. So the moment of inertia will just be the mass multiplied by the distance away from the axis of rotation, which in this case is just r/2, and then we square this. So this is just m times r/2 square, and then we have the other sphere which has the same characteristics. This gives us m/2. Right, for this, the big R, which is just the difference between the the distance between the two nuclei is given as 2 times 10 power minus 10. Whereas on the other hand, for the small r, this is the radii of the nucleus. This is 2 times 10 power minus 15. Now to compare the energies, right, between the y and the rotation about y and rotation about x, we take Ey divided by Ex. This gives us h bar square over Iy divided by h bar square over Ix. It's just Ix over Iy. And as we know, Ix over here is just m over 2 times 10 times 2 times 10 power minus 10 square. And for Iy, it's 4 over 5 times m times 2 times 10 power minus 15 square. And the resulting answer from this about 6.25 times 10 power of 9. And we can see that the energy of rotation about the y-axis is 10 to the power of 9 orders of magnitude larger than the energy required to rotate about the x-axis. So it is inhibitively high, much higher than the other rotation, and therefore it is usually very hard to access by the molecule.